All right, line M1, learning test 2, we're going to talk about alternator theory, describing the operating principles of our three-phase alternators. We're going to go through a couple of formulas that we're familiar with already, one that we have talked about ad nauseum already this year, E.g. is equal to K, phi, and N, which is going to go and tell us how we generate values of voltage, but we're also going to go and deal with one that we probably have not seen since possibly first year, if not second year, and that's going to be this one here, which is going to be dealing with frequency, where frequency is going to be based upon the number of field poles multiplied by the speed in RPM over top of 120. Now, there will be times where you're going to see the same formula written as F is equal to P times N over top of 60. And the difference between that formula and this formula, because they're really looking at the same thing, is that this one here that's over 60 is talking about pole pairs. Whereas this one over here is talking about the physical number of poles. Let's just go and, make a quick little illustration to see what this looks like. What I could have is I could have this machine over here, like that. If I were to count the individual poles itself, here's a north, south, like that, I would go and count the individual number of poles, and I would say that there's 4 poles. If I wanted to go and use this formula here, I would have to go and count the number of pole pairs. A north and a south together makes a pole pair off of these ones. So just pick one that you want to go and stick with. I generally do with the pole pairs one rather than the individual number of poles, but either one is equally as correct, because really if you take a look at pole pairs, that's going to be half as many over half as much, which is really going to go and give us the exact same answer. But mathematically speaking, makes absolutely zero difference from one to the other. Okay, let's talk now about this formula itself. When we take a look at this formula over here, what it shows us is that we have got this relationship between speed and between actual physical frequency of our components themselves. In this case, the frequency of the voltage that's going to be coming out. If we look at that N relationship, we see it shows up inside of 2 separate formulas over here. One of these that's going to be for frequency, one that is going to be for voltage. And so adjusting the speed of any sort of an alternator is going to go and adjust 2 things simultaneously. It's going to adjust my voltage, which is a good thing because we do see voltage that sags away in a lot of cases, but it's also simultaneously going to go and adjust my frequency. And that's a really, really bad thing, because when frequency changes, we get a whole pile of other effects that are going to go and change. When frequency would vary, all of our XLs and our XCs are also going to go and vary, and they're going to vary greatly, which means that total impedances of loads, all sorts of stuff goes crazy. We don't want to move off the 60 hertz system. The other thing that we have 60 hertz for is it is a really easy system for us to go and deal with a lot of our timing. Things like computers and data that deal with data that's going to be put out in specific little bursts. We need to make sure that that data is able to be picked up and read by other things that have the same sort of timing. So we just don't want to go and screw around with the frequency. Therefore, we're not going to go and screw around a lot with the speed of our alternators. We're going to take it to where it's rated, and then after that, if we need to adjust our value of voltage, we have to go and select something else out of here. Really, the only thing that we see that we could select out of here would be to go and change the phi, or the flux that's going to be on my system, because if I change anything else, speed, the frequency changes, and my machine, I'm not going to get into my machine and physically change the structure of that machine. The air gaps, the type of metal, the windings, all of that other type of stuff just is not practical. Let's talk a little bit about voltage regulation as well. Whenever we have got our alternator running unloaded, we are going to go and have voltage. Okay, so we're going to have some sort of a voltage over there. Now, as we go and increase the amount of load or the amount of current that we are going to take off, and we are talking stator here because most of ours we are going to go and have that rotating field, so all of our windings come off the stator. When I take a look at this, I see that as my I goes up, I'm also going to go and have an increase in V. And the V that we're talking about here is going to be the voltage drop across the windings. If I take a look at each of my physical windings, as the current goes through, increases, these windings do have a fixed value of resistance. They also have got a fixed value of XL, inductive reactance. That is going to go and be part of them as well. Altogether, the R and the XL is going to go and give me a Z, and I can go and substitute that Z into this formula over here and say that my voltage is equal to my current multiplied by my impedance that I'm going to go and have. So that, sorry, not my current, but my voltage is going to be equal to my current multiplied by my impedance. That V that we're looking at is going to be the volts that are going to be dropped before it ever leaves the machine. I might be generating a value, and we're just going to go and give ourselves a value of 120 volts per coil. But if I lose, 8 volts before to my IZ or my IR drops inside of there, I'm only going to be exiting this thing with 112 volts. So we see just this relationship or this drooping type of voltage that we are going to go and have off of these. Once again, we are going to go and have some formulas to go and deal with these, and it's going to be the same format that we have talked about before, where they call this thing percent regulation. We will have percent voltage regulation for these based upon the values that we have at no load. That's going to be this one over here, E no load. This one over here, which is going to be my full load, whichever value we take off of here. We'll talk about the different curves here in a second, but my E full load over there. The formula itself is going to be my no load minus my E full load, and it's really hard to read it inside of your binder there because it's kind of a crappy reprint over there, all over top of my E full load over there, which is going to go and give me my percent voltage regulation. We multiply that by 100, and then we know what percent this thing is going to go and look at. It should not be very, very great, from no load to full load. We don't want to see a massive drop that we are going to go and have inside of here. But that drop can get affected by the type of load that I'm going to go and attach onto my gensets. So over here, they show 3 different curves. The first curve that they show is one for a unity power factor. We're going to start by analyzing that one, where we're just saying, look, as we increase the amount of current that we are drawing out, that's this over here, we are going to go and have only resistance, and therefore I'm going to go and drop a certain amount of volts. These volts over here are the volts that I have lost off of my winding before it has ever exited from my machine itself. That's pretty normal. That's a pretty typical curve over there. If I go to something that has got a lagging power factor, and they're giving us an 80% lagging power factor over here, I'm going to get an even greater drop. Okay, so now we're going to go and have this amount of volts that we are going to go and drop, and it's going to be based upon an impedance that we are going to go and have. If I had go to a leading power factor, we've talked about this before, that leading power factors are highly problematic for us. We talked about how they raise the voltages on transformers. They also raise the voltage on alternators or on generators themselves, and this is a dangerous thing because we put too much voltage to stuff and we let the magic smoke out of the inside of those components. So what we see off of this one is that now we're going to go and have a rise that's going to happen before we ever leave that machine. It's going to go and aid, it's going to go and add on to our value of voltage. There's a calculation that they show below this drawing here as well for how to go and take a look at your percent voltage regulation. We want to have a very low percent voltage regulation, which means that we're not changing a lot between no load and full load. Let's talk about this load power factor and how it changes those values of voltage. The first thing that we are going to do is we are going to go and say that there's a couple of constants, and these are formulaic constants. First of all, EG is equal to my K, the machine type. I'm not going to change that. Phi, my field type, so the type of flux that I have off the field, and N, my rotation. If I have got the same machine with the same amount of flux and the same value of rotational speed, I'm going to go and have a same EG. I want you to note that for every single one of these, I have got the exact same length of my EG that I'm going to have, or the voltage that I'm going to go and generate. What I'm going to see off of that as well is that every single one of these has also got the exact same triangle that is going to be associated with it. This one over here has got a triangle. This one over here has got the exact same triangle, and this one over here has got the exact same triangle that's going to be associated with it as well. Those triangles are based upon physical components that we are going to go and have. They're based upon the K, the type of the machine that we have, the amount of impedance that I'm going to go and have, and the amount of resistance that I'm going to have inside of my windings. Because when I take a look at this value here is the volts that drop over top of the R of the winding. This is going to be the volts that I'm going to go and drop over top of the inductive reactance, or the XL, which altogether gets me this value of Z that I'm going to go and have across there. So how does this go and affect the value of terminal voltage? Well, the terminal voltage is what we're measuring along the bottom. If I've got a unity power factor, that means all of my current is in line with all of my voltage over here. So I see my current and my voltage are going to be in line. As soon as I go to a leading or a lagging power factor, I'm going to go and have, in this case, lagging. My current is lagging my voltage. Therefore, my current that is going through the actual windings is going to be lagging as well. Note that those two are in parallel. Same with on this one here, where my current is leading. These two lines over here are going to be in parallel as well. We've got a couple of things that are going to go and be constant inside of here. We've already noted them. They're going to be the value of voltage generated, because it is based off of physical components, and it's going to be this triangle, because it's based off of, once again, physical components that we are going to go and have. What we're seeing happen in here, and I'm just going to see if this works with my mouse. I'm hoping this thing does, but who knows? Sometimes this thing does get a little bit glitchy. Can I adjust? Let me just try this one here. That one there might work. I can't adjust where the click part is there. I was hoping that I could adjust the anchor, for the rotation that you can on some of these Windows type of things, and I was hoping to show that we can, as we rotate, instead of rotating around the central axis, that what's happening is that this point over here was staying solid. I'm just going to have to skip on that because that doesn't work, and we'll just do it the old-fashioned way, which is to say that this point over here, we have to treat this as if it were a hinge. Every single one of these over here, I see that I've got my value of generated voltage directly attached over onto this, and all we need to do then is we got to say, if I've got that same value of voltage attached onto this triangle, if I keep the triangle straight, I end up with this value of terminal voltage. Okay, my regular value of terminal voltage. If I go and have my generated voltage in my triangle, but now I go and twist that triangle in like that, I'm going to go and have a shorter terminal voltage. My amount of terminal voltage is going to go down. We see that reflected right over here on that lowered value of terminal voltage that we have. And if I were to take a look at my last one down here, my last one shows that if I keep this anchored together and now I twist this triangle out like that, because it's matching this current line over here, I'm now going to have a much larger value of terminal voltage. That in a lot of cases is actually going to go and be larger, higher than what I have for my rated full voltage. This is my rated full no-load voltage that I would have there. Obviously, it's going to be a very dangerous thing to go into an overvoltage. Insulation starts to go and break down. We start having issues that come as a result of that. There's another thing that also goes and affects our total amount of voltage that we're going to go and get out, and that's going to be something called armature reaction. And what armature reaction is I want you to think about armature reaction as being grabbing force of rotating current. If you have ever worked around, anybody that's chipping wood or anything like that, what you'll see inside of a wood chipper is that there's going to go and be two main rollers that are going to have a bunch of teeth going around the outside like that. Bunch of teeth that are going around the outside like that. We're looking at these things from the side, and then what I'm going to do is I'm going to go and rotate these things towards the center, and as a result, when you go and feed branches and sticks into there, this is going to go and grab them, and it's going to go and pull them through, mash them through the blades of the chipper, otherwise they would just kind of bounce around off of it. We get the same sort of thing that is going to be happening with the armature reaction. It's not a wood chipper, but it's a close enough analogy that we can at least look at the way that the magnetic lines are grabbed and are going to go and be focused. If we take a look at this first one over here, we know that lines of flux are going to want to go across from north to south on every single one of these, north to south, north to south. This over here is going to be a unity power factor load, and if I have got rotating lines of flux that are going around those conductors over there, what's going to happen is as I emit this from the North Pole, this line of flux is going to grab it, rip it around. It's going to start heading back across. This one's going to grab it and rip it around over here. And I've got an equal amount of pulled up, an equal amount of pulled down. It's going to go and give me some counteracting, some motor effect off of this thing, but it is not going to go and be unbalanced, because if I take a look, I see that I've got the same amount up, the same amount down. If I go to a lagging power factor, the lagging power factor is going to go and set up another fake pole. Okay, so this over here is going to go and give me a bit of a fake pole. This over here is going to go and give me a bit of a fake pole as well. And what I want you to look at now is that these here are rotating around. They're pushing out like this, which means that as I fire lines of flux in from my north over here, it's going to be harder for me to stuff them through, and some of them are actually going to get grabbed and carried around the outside. This one here, grabbed, carried around the outside like that. Actually, I wanted to draw those two in blue so it's easier to see them. Grabbed, carried around the outside, and then in. This one here, carried around the outside, and then in. What this does, this means that my generated value of voltage, EG, is equal to K, phi, and N. This value of phi has gone down because I'm going to have less flux that's traveling through the center. The top one over here, the flux was distorted, but it was all still going through the center. This one over here, it's now going to go and lose some of those lines of flux, and it's harder to push through against this, rotation that's over there. If I go to a leading power factor, that leading power factor is going to go and give me now rotation on this one like that and on this one like that. This is just going to be off of the generated values. Once again, don't stress too much about trying to envision where they come from. We're just explaining why these terminal values of voltage are going to go and increase. What we're seeing over here is that lines of flux that normally would have been evenly differentiated across, like on the top one over there, are now going to get grabbed and they're all going to get mashed down into the centers. All of these lines are going to get mashed down into the center. And what that's going to do is right over here, I see that I've got a much greater amount of flux. What has not changed has been the total number of lines of flux, but what has changed is how we are going and lining those up. And we're going to go to another formula that you should be well familiar with at this point, and that one is going to be EG is equal to BLV. This one over here tells us once again that the amount of generated voltage we're going to have is going to be based upon physical things, speed, the velocity, length of conductor, and then this B over here, which is beta, which is going to be flux density. And flux density just talks about the fact that it's the same number of lines of flux, we've just grouped them closer together. This over here describes a much greater amount of flux density. We've mashed them together because we've kind of like in the analogy of using that tree shredder, we've grabbed them and we shoved them all onto the inside over here. So my flux density has increased, same number of lines of flux, but they're closer together where they cut through these conductors. Therefore, the amount of voltage generated is going to go and become larger off of these as well. So all of this, what we looked at over here, what we looked at over here, these triangles and all of these can just be summed up quite simply, and it's not something that, once again, you need to be extremely worried about, having to go and describe on a day-to-day basis. We just need to know what the effects are going to be, because then we can go and predict what's going on, as well as we can go and see what's happening when we're sent in to troubleshoot something. Is my voltage on my genset high? That's weird. My voltage usually should be lower, therefore I'm probably looking at that something's been added. That's going to be a leading power factor. Same with if my voltage is really, really low, do I have a lagging power factor? You can go and do some checks. We're going to learn about in PQA about how we can go and use like crest factor and stuff like that to go and check for things like harmonics, etc. Know what's laid out for you really, really simply on page 19. There's 3 bullet points. They say that the greater the load, no matter what the load is, so if it's inductive or if it's capacitive, if it's leading or lagging, or if it's just strictly resistive, the greater the amount of current I pull, the greater the voltage drop I'm going to go and have. And then they say with the lower the power factor and the lower the power factor. Again, I find this language to be a little bit confusing. Maybe you don't. Maybe it's just me. But I find it easier just to say that with more lagging power factor. I've just crossed out the first 3 letters there, the lower that they have there. I just have with more lagging power factor, the greater the voltage drop, and with more leading power factor, the greater the voltage rise. Technically, they are correct in the way they write it out. It's just a harder thing to visualize like that. Last thing that we have in this one here is automatic voltage control. Because my load is going to be changing consistently, I'm going to go and have changes that need to be dealt with all the time. And I don't want to have to go and constantly readjust my generators. I need something that's going to automatically do so. This is going to be automatic voltage control. Automatic voltage control is just going to be something that is going to have a combination ammeter that is then going to be connected with something that's going to be able to change the amount of current that I'm going to go and send through my alternator field. I mean, really, if you think about it, you can even design these, conceptually quite easily just with your knowledge of electronics, right? The greater the amount of current that's going to go through, I can just use a transistor and I can go and use that to amplify, the amount of field current that I'm going to go and send through or something like that. It's just it's a way that is going to go and respond to load changes. When I draw more, it is going to go and give me more field current to bring my voltage back up. And when I draw less, it is then going to go and give me less field current, which is going to give me less flux, which is going to drop my voltage back down to where it is so that the voltage doesn't end up being too high. All right, that's it for this one.